one-stop solution for ADAS and autonomous driving test solutions. So my name is Heidemann, CEO from SET, and you heard about Michael Konrad just a minute ago, and you will see him right there. So it's one-stop test solutions for autonomous driving. It's a multi-domain HIL and sensor simulation, what we want to talk about. And we have only 20 minutes, and we want to give you an insight into HIL, into really roughly about the architecture of the systems, and then go into simulations of all these multi-domains, what we need to do that one test solutions. So a short overview of SET. We are one of the alliance partners and member of the ADAS iiT consortium, and I'm jump over that. And you find us in the south of Germany and a couple of sites in Germany and East Hampton in the United States. Konrad Technology, and you probably hit it, I wasn't there, but no, you didn't. Okay, so Konrad Technology in Radolfzell is a company from Germany with many sites all over the place, 300 employees in 7 countries, 12 offices, founded in 1993, I think, and you heard a lot of, for all the partners who were in the room, we were yesterday at the keynote in the morning, you heard a lot of the foundings and what this company does. With the core competences in production out of autonomous testing, radar testing, sensor fusion testing, recording, and the recording solution we just heard a minute ago. Both of our companies are part of the ADAS iiT consortium, and the ADAS iiT consortium is a consortium of 4 alliance partners who put together a initiative to test ADAS and autonomous test solutions. So all of these companies, they really sticking with their core competences. So SET provides the technology for HIL and signal conditioning systems, Konrad Technology about this radar, sensor fusion, Lidar, all what we will hear in a minute, S.E.A for GNS, GPS simulation and car-to-X communication, and measX, the fourth company, data management to handle all this huge amount of digital data. Together we form a consortium with 450 engineers worldwide in 7 countries and 17 offices. So let's stop into the solutions. So one-step test solution. So what is the challenge? And I'm just make sure that I don't tear out that cable here. So what is the test challenge? Autonomous driving is basically the fusion of so much information we never had before in a car. We have multiple radar sensors around the car, between 8 and 12 radar sensors for near field and far field detecting of targets around the car. We have camera detections, sometimes in the front, sometimes around the car to do surround viewing. We have acoustic sensors for the pretty near field. We have Lidar sensors, very high precise Lidar sensors for target identification in front of us and in the surrounding of the car. And the challenge is now for both sides, for the testing as well as for autonomous driving, that car needs to collect all these data and make up their mind where it goes and where the right way and the safe way is. So the challenge is to test it on the other hand is we need to have a multi-domain expertise because we have all these sensors, and beside the fact that we have communication, analog I/O, digital I/O, LVDS, broader reach, so it changes dramatically the systems and the system architecture of an HIL system since we need RF know-how up to 80 gigahertz. We need optical expertise for Lidar and camera simulation that we are able to simulate these targets to the system. On the other hand, we have these analog high-speed digital buses, expertise in handling LVDS signals, as we heard, to handle all these big data coming from cameras, lidars, and radar sensors. And then the car needs to communicate with the world, and it needs to know where it is. So we have GNS simulation, GPS simulation, and car-to-X communication, what we need to stimulate to that system. And we need to put that all together under a scenario simulation. So we need to simulate that scenario around that car and make that obvious to all the sensors and obvious to the system which we want to test. So taking that system on the left side, and we're talking about connecting an ACU or multiple ICUs. What we use usually is an HIL simulator to simulate that environment to that ECU and the unit under test. And for the electrical purposes, we have CAN, FlexRay, broader reach, so all these communication buses we know already. We have discrete I/O and analog and power. And beside of that, we have the fact that we do need inject faults on these ECU internally to make sure that we reach the safety critical level we need to reach with that. And we need to do that all in real time. And to adapt to the UUT, we're using SLSC as the platform signal, switch signal and load signal conditioning system from National Instruments, and behind that, a PXI system. And to communicate now with the model, we put a very standard application on top of it, running it in real time on a PXI system as a sandbox to put all these models in it. And when we talk all these models, it's a model about the car, it's a model about the road, it's a model about the behavior of the driver. It could be traffic models, it could be any other scenario model, what we need to run it in real time. And to be able to communicate with the other side of the ECU, so the real world, how the car looks into the world and recognizes the world, is we need to be able to simulate all these physical targets. So we need to be able to simulate a radar target, a Lidar target, acoustic targets, and so on, and we come to that later. So first step, let's a little bit look into the architecture of an HIL system. We have the GUI, the interface to the user. We run the HIL core, which is very standard most of the times, in real time on that PXI system, and put on top of that very standard applications like IPG CarMaker. We have an FPGA level for high-speed simulations in 80 megahertz rates and analog, digital, and buses. And to do the signal communication and faulting, including the breakout, we're using SLSC as the platform of our choice, and then connect that to the UUT. So again, it's PXI and SLSC what we use in these HIL systems. So what we do is we take very standard as the sandbox and take a scenario model application, which could be in this case IPG CarMaker, and we run that in real time on Veristan. And from that Veristan application, and here only as an example, we take radar and a video for an example. We take these informations like the radar information of the target, like the video information of the target, and put these to the simulators. These simulators produces a target which is pretty much the way a real target looks like, and the ECU sees over its radar sensors and camera sensors, for example, these informations, and feed these informations back. And then it decides if it needs to brake or overtake or whatever. And this information, that decision from that system on the test, we feed back to the system and into the model, so we have a closed loop. So if the ECU decides to brake, we manipulate the model in real time and slow down the scenario, or we overtake within the scenario. And doing that, we are able to reach to a real-time simulation system to doing that. So saying that is, we have the ability to simulate these models to the ECU. We are able to manipulate the ECU or the multi-targets in real time on board, even on PCB level, to be able to certify these systems and test all these monitors. And on the back end, we have management systems like TestStand for test cases or any other management system, and feed these informations to data. On the other side of the system, which is the target simulations, we have now the need of physical, be able to do physical simulations. And then with that, I hand over to Michael, and he will give you an insight about these physical simulations. We do that all in real time, right? Like HIL. Here we go.
Thank you, Frank. I was getting nervous with the schedule. We can talk for hours. Yeah, thank you for introduction. I'm Michael Konrad, the CEO of Konrad Technologies, and I want to jump a little bit more deeper in our simulators, camera, Lidar, and radar. And what you can see here is a typical system for simulation of Lidar targets. How does it work? So on the left side, you have a Lidar unit. The Lidar unit is flashing light. And then the unit is measuring the time of flight until you get a reflection back, and also measure the intensity, so the reflectivity of the target. So to simulate that, we have a detector which detects the emitted light. Then we transfer that in a digital domain, we delay it, and after a certain time frame, we just flash a reflection light back. With that technology, we are able to generate complete point clouds. And here you can see a video. Don't look to the artifacts on the lower area. We simulate here 2 blocks, and we let some objects just driving from left to right. On the right side, you see the intensity map. So if you have a video stream or if you have a simulator which can generate point clouds, we just downstream them and can simulate a complete point cloud. And what you are seeing here is definitely the feedback of a LiDAR sensor. Yeah, another thing is radar target simulator. So it's nearly the same technology. So what we're doing, the radar sensor is sending out a chirp and an earth signal, and then we wait for the reflection of the object. So we got back the timing, we got back the intensity of the reflection, and we got a speed information, we call it Doppler. And here on the right side, as Frank mentioned, we simulate all those scenarios in CarMaker. CarMaker is sending this information to our radar target simulator. And when the radar system is emitting the signal, it comes in our radar target simulator. And we put relative speed on it, the RCS, that's the intensity of the reflection, and the distance, and just send it back to the radar device. So we can very easily simulate objects. And here is a demonstration how a radar target simulator looks like. We do not have it here at the booth. We have a parallel trade show in Germany. So what we're doing in the white black ball, there's inside the radar target simulator, the radar device, the sensor. On the left side, you see the black thing. That's a moving horn antenna. So with the moving horn antenna, we can simulate the angles. And the white-black box has another feature. We can temperature the sensor from -40 to +85 degrees. So you can do all the simulations under full temperature range. Here we show in a demo just one target, but we can have up to 4 targets and additional 4 following targets in the same angle. But then the hardware looks a little bit more complex. Here you can see the moving arm. And the challenge is here to have that arm high dynamic, because when a car is coming from the side and just driving in the field of view, you have to simulate that with a very fast and dynamic moving horn antenna. Camera target simulation, in principle, Jeff talked about a little bit. We got all the information from CarMaker and we project on the screen the scenarios, and the camera is looking to the screen, and so we can simulate the complete environment. And then we acquire the data with the LVDS interface, but Jeff talked already about how we do it. Here's another thing. Instead of presenting a screen, we can do directly data injection. So we inject the data behind the sensor chip. We inject the data directly to the ECU and can also simulate different video streams and scenarios. And that's how it looks like. It's, yeah, Jeff told already about that. I think we can jump over. And here's a complete scenario created in CarMaker. So you see on the left side the response of the radar. On the right side you see Lidar. At the bottom you see, left you see the response of the camera. And we are passing the object and you see all the feedbacks of the sensors are changing. And I think now as an ambulance coming from the right side, we got informations via Car2X. So the car will stop until the ambulance will pass. Yeah, it's stopping now. No, it's not stopping. Yeah, it's stopping. That would be a mistake, yeah? And that's exactly why we are testing this. And you have seen all sensors responded to the simulation. So that was really the target simulators in front of the LiDAR, in front of the camera, in front of the radar sensor. And so we could really simulate the complete virtual environment. Yeah, and finally, this is a complete system. It's already 2 years old. It was during a trade show in Germany. So on the left side, you see the target simulator. Here, the camera simulator. So we have a very small screen with a relay lens between. So you do not need the big screen anymore. In the middle, we have the radar target simulator with the absorber box. And on the right side, we see the hill system from SET. Data recording, you talked already about that, but I would add something. But if you're interested on, we're at the booth, yeah, you can visit us. And thank you for your time.